Hi everyone, welcome to the video lecture for Class 2 for PH 125. Today we'll be talking about units, dimensions, and significant figures. Okay, so just to let you know, at the start of every new chapter, I'll have a slide that looks a lot like this one. It'll give you the chapter title and then also the learning outcomes for that particular chapter. So we're starting off at Chapter 1, which is Introduction to Physics. Okay, so first big question we need to answer here is, what is physics? I will tell you this is a question that I get asked all the time, and it's still kind of hard for me to answer. Particularly, like, my parents will be like, what is physics? It's very hard to answer in general, but so here's our best attempt. So physics, it comes from Greek and Latin words, which both means natural things. And essentially, it's just the study of laws and relationships that can be found in nature. And it turns out that these relationships can be expressed mathematically. And then we can relate the observed world and experimentation to these mathematical expressions and compare them. So that's kind of the overview of physics from a, 10-foot view. So that's the big picture of physics. A little bit more in detail, we can talk about different areas of physics. So for example, this semester we'll be focusing a lot on classical mechanics. So classical mechanics is the study of macroscopic motion. So that's what we'll be working on this semester. Next semester we'll work a lot on electricity and magnetism, and also quantum mechanics, which is the study of subatomic particles, sub meaning smaller than, so really it's things that are smaller than an atom. Some other interesting areas of physics include the theory of relativity, which was, which is probably the thing that Einstein is most famous for. And then also astrophysics and cosmology, which is super interesting. It's the study of the universe. There are many other fields in physics as well. Okay, so learning physics, how do I go about learning physics? I know that physics tends to have a bit of a reputation for being a challenging subject, but don't panic. That would be my first, bit of advice is don't panic. You're going to get through it. Don't worry. So some ways that you can help ease yourself into learning physics, some steps you can take. First, read about it. So that would include watching these lectures. So it's not really reading, but reading through the slides from these lectures, I think would be a good place to start with reading about it. Sometimes I think the textbook gets a little overwhelming. So if you start reading the text and you feel overwhelmed, maybe go back to the slides instead. Untangle it, so watching these video lectures helps, of course, but then more so during our discussions in class as well. Play with it, so that's what you'll be doing in labs. So hopefully you'll be working on concepts that relate really closely to the material we're covering in class every week. And so you should feel like you're getting, a hands-on experience with the experimentation piece that goes hand in hand with the theory piece that we cover in this course. Challenge yourself, so that's working through homework problems and practice problems, which we'll be doing in class. And then close the loop, so come talk to me. I have office hours. Send me an email, let me know if you're having any trouble with anything, or if there's something that's confusing still for you. Also, we will have physics tutors, and so you can go see them. Really wonderful physics majors who are very happy to talk with you about anything to do with physics. So just a reminder, we will be using algebra, trig, and geometry. We did a little review in the first class, but if you would like a little bit more review, if you're feeling a little fuzzy on those, you can see Appendix A in your textbook. And last thing, and I have it in bold here because it's important, the last thing here is just to emphasize that physics is really about understanding relationships and problem solving. And it's not algebra. So it's not about plugging in numbers to an equation. So this tends to be a bit of a it can be a bit of a hang up, a little bit of a downfall. It's, I think, probably where physics gets its reputation for being challenging is, there's this temptation to just kind of find problems that look similar to the problem you're being asked, plug in numbers, and then, maybe you didn't quite understand the relationships you were applying, and so it doesn't work out. And so it's really not the best strategy to just look for similar looking problems and try to plug in numbers. Really highly emphasize trying to understand relationships, understand the steps in solving a problem, and that will help you solve other problems that are a little bit different. So no problems or two problems are going to be exactly the same. They might be similar, but maybe, there will be a little piece that you didn't quite get the first time if you were just plugging in numbers. So I highly recommend treating physics more like solving a puzzle, putting the pieces together instead of just plugging in numbers to equations. We do give you equation sheets. There's no need to memorize equations in this course, and so that should give you a pretty good idea that it's maybe not as important to be able to put the numbers into the equations. It's much more important to be able to, fit the relationships together. So with that in mind, I would highly recommend, if there's a question when we're solving a problem, if you don't quite understand the connection between two steps or, one of the equations that we used, please let me know, stop me, send me an email. That's really important information. So don't just think, oh, maybe that wasn't that important. Trust me, it is. And so anything I can clarify, I will be happy to do that. Okay. So getting a little bit more into, kind of the nitty gritty here. So when we're talking about physics, I mentioned that it's a lot of, creating this theory, these mathematical relationships, and then relating them to experiment. And so to do that, we need to take measurements and we need to have units for our measurements. We want those units to be consistent so that we can compare our measurements with other scientists or with our theory. And so that's why we use SI units. So the SI unit of length is the meter. Previously, this was measured as a relationship between the equator and the North Pole. Now it's measured more accurately by a relationship to the speed of light. And just for reference, 1 meter is about 3.3 feet. Okay, next we have the kilogram, which is the SI unit for mass. Previously, this was defined in terms of the standard kilogram, which I have pictured here. Which was an actual it was like a punk of metal that was 1 kilogram of that metal, and it was kept, all vacuum sealed and safe. But actually very recently, especially in the world of physics, in 2018, it's just super recent, the kilogram was actually redefined in terms of Planck's constant, which is just a very well-known constant in physics. So it's not like it changed or anything, it's just how we define the kilogram was changed from this, piece of metal to something that's more, it will stand the test of time a little better. Just for reference, if you want to know what a kilogram of mass is, 1 quart of milk is about 1 kilogram. The average adult human is about 70 kilograms. Okay, lastly, the SI unit for time is seconds. And previously this was defined in terms of the solar day. So 1 day is 24 hours, and so that would be 86,400 seconds. And that was how a second was defined. Now, again, we have a more precise measurement. It's actually defined in terms of the decay of cesium in an atomic clock. Okay. And so these SI units are really great. They're really useful to us, but sometimes they can be a little bit too big or a little bit too small for the thing we're trying to measure. And so we actually take base units and then we multiply them by these unit prefixes to get, scale up or scale down these base units in terms of powers of 10. Okay, so base units here, meters, grams, and seconds, M, G, and S. So you'll notice here immediately I'm talking about grams. In the SI units slide, 1 slide ago, we talked about kilograms. So actually we've already used these unit prefixes. So it turns out a gram is a little bit small. It wasn't that useful, and so the SI unit was chosen to be the kilogram instead. And so we've already been applying these unit prefixes. Kilo, you'll see in the chart right here, is 10 to the third. It's a K, so kg is kilograms, and it's 10 to the third grams. Alternatively, I could divide both sides of this equation right here by 10 to the third, divide by 10 to the third. I would get a 1 gram on the right-hand side, and I would get 10 to the minus third kilograms on the left-hand side, and so that tells me that 1 gram is also equal to 10 to the minus third kilograms. Okay, Some other examples here. Nanosecond, 1 ns. If I look at my chart over here, I see nano right here. And so nano is 10 to the minus 9. So 1 nanosecond would be 10 to the minus 9 seconds. Alternatively, then, I could say 1 second is 10 to the plus 9 nanoseconds. One more example here, I have 2 centimeters. This one you're probably pretty familiar with. Centi is C in my chart, it's 10 to the minus 2. So 2 centimeters is 2 times 10 to the negative 2 meters, or 2 meters would be 2 times 10 to the positive 2 centimeters. Okay, so some other unit prefixes that we'll be using often on this chart. Usually we will stay in about this range. So we want to go about like that. So from nano at the bottom up to giga at the top. Generally we do, steps of 3. So the centi we do use, but deca, not so much. Deci, not so much. Hecto, also, no, not very much. Okay. So here we go. I have the unit conversions up here at the top of the slide. And we want to know how many milligrams are in a kilogram. Okay, so let's take a look at how I solved this problem. I said 1 kilogram is 10 to the 3rd grams, which I got right from the top of the slide. And then I kind of split this out. So 10 to the 3rd times 1 gram. Those two things are equivalent, right? Those first line and the second line. That's pretty obvious. Well, then I just plugged in 1 gram is equal to 10 to the 3rd milligrams. Right in there, right, for 1 gram. So I plugged in 10 to the 3rd milligrams, and I have 10 to the 3rd times 10 to the 3rd, which remember when you multiply things that are raised to a power, the powers add, right? So I end up with 10 to the 6 milligrams. It's tempting to multiply them together and get 10 to the 9, but you actually want to get 10 to the 6. So then that tells me that my answer should in fact be B. All right, so now converting units. So we've already been converting units by applying these unit prefixes, but it's often necessary to do a more complicated unit conversion. So for example, if you're going from feet to meters, something like that, it's not as straightforward because you don't just have those powers of 10, which are so lovely to work with. Okay, so instead of using the kind of intuitive approach that we just used with our powers of 10, we'll actually want to apply a more general approach. So first of all, let's take a look at our intuitive approach for a practice problem. How many millimeters are in 2 meters? Okay, so here's my intuitive approach. First of all, I write down my conversion factor from the chart on the previous slide, which told me that 1 millimeter was just exactly equal to 10 to the minus 3 meters. Okay, and then from there, I'm going to divide both sides by 10 to the minus 3. And so that would tell me that 10 to the 3rd millimeters would be equal to 1 meter. Okay, and then from there, I'm just going to multiply both sides by 2 to get what I'm looking for. And so I can just go ahead and say that 2 times 10 to the 3rd millimeters is equal to 2 times 1 meter, which would just be 2 meters. Okay, and so then that's exactly what I'm looking for, right? So how many millimeters are 2 meters? And that would be 2 times 10 to the 3rd. Okay, so that's our intuitive approach. But what about a more general approach when we aren't just working with these powers of 10? Well, then we want to use the fact that anything multiplied by 1 is just going to be equal to itself. So, 10 times 1, it's just 10, right? So multiplying by 1 is pretty straightforward, and we're going to use that to do unit conversions. Okay, so here's my general approach to the same practice problem. First of all, I want to look up the conversion factor. You can look it up online, you can Google it, or you might look it up in a chart in your textbook. So I'm going to write down the same conversion factor that I already had. 1 millimeter is equal to 10 to the minus 3 meters. That's my starting place. Now, the next thing you want to do is to use that conversion factor to write out a ratio that's equal to 1. So how am I going to do that? Well, before when we did our conversion factor up top here, I divided both sides by 10 to the minus 3. Now instead, I'm going to divide both sides by 10 to the minus 3 meters. So then all that's left on the right-hand side of my equation is 1. So I get 1 millimeter divided by 10 to the minus 3 meters, and all I'm left with is 1. Alternatively, I could have divided both sides of my conversion factor by 1 millimeter. In that case, I would get a 1 on the left-hand side, and on the right-hand side, I would have 10 to the minus 3 meters divided by 1 millimeter. Okay, so now I have two possible ratios that are both equal to 1. Next thing I want to do is I want to use those ratios, which are equal to 1, to just convert my units. So starting out here with 2 meters, I would say 2 meters is equal to itself multiplied by 1. But now instead of just writing 1, I'm going to use my conversion factor, and I'm going to pick the ratio that cancels the units I don't want and leaves me with the units I do want. So in this case, I want to cancel meters and I want to be left with millimeters. So I'm going to use this version over here on the left-hand side, 1 millimeter divided by 10 to the minus 3 meters. And that is equal to 1, right? So 2 times 1, 2 meters times 1 is just 2 meters, right? Okay, my meters cancel. I'm left with millimeters, which is what I want. And 2 divided by 10 to the minus 3 is 2 times 10 to the plus 3. And I'm left with millimeters. That's the same answer as before. Okay, so that's exactly what we're looking for. And this is a general approach. We can use this to convert more complicated units, and we'll look at some examples of this in class. Okay, so now we want to talk about dimensional analysis. So first we need to define what is the dimension of a quantity. So the dimension really just describes what type of quantity it is that you're measuring. So the easiest way to talk about it is really to just look at some examples. First of all, 100 feet has the dimension of length. So even if it was 100 meters, it would still have dimensions of length. It's independent of the units, it just tells you about what it is you're measuring. And we denote the dimension of length with a capital L in square brackets. 50 kilograms has dimensions of mass, which is capital M in square brackets, and 2 hours has dimensions of time, which is capital T in square brackets. And so then what is dimensional analysis? It's really just applying this idea that both sides of an equation have to have the same dimension. Okay, and that tells us that the equation itself is dimensionally consistent. So whenever the dimensions on the left-hand side match the dimensions on the right-hand side, the equation itself is okay. So this is a good way to check your equations before you plug in numbers to make sure that you've done your algebra right. Do you have matching dimensions on both sides of your equation? Okay, so for example, the previous slide we said that 2 meters was equal to 2 times 10 to the third, or 2,000 millimeters. And so I can check this equation. This one's pretty easy, right? So we have meters on the left, millimeters on the right, they're both length. And so this is dimensionally consistent. Okay, and so that's what we mean when we talk about dimensional analysis. All right, so it's important to note here that dimensional analysis, it's really useful. It's used often in unit conversion and also can be used to help you solve a problem when you know the dimensions that you're looking for. But it's not everything in a problem, so checking dimensions is important, but I could also write 2 meters equals 3 millimeters, which obviously is not right since 2 meters is 2,000 millimeters, right? So it doesn't get you all the way to the right answer, but it's really a great check, helps you make sure that you're on the right track in solving a problem. Okay, so quick question. What is the dimension of the measurement 60 miles per hour? Well, miles have dimensions of length, which is capital L in square brackets. Hours are time, which is capital T in square brackets, so I get L over T. Answer C. Okay, next up we have significant figures. This is where we'll be wrapping up today. So significant figures tell us about how accurate a quantity is that we've measured. So realistically, the ability with which we can measure a quantity accurately is always limited. So for example, if I look at a pencil that I have here next to a ruler, I would say, okay, if I draw my line down from the pencil eraser, it's somewhere between 8.4 and 8.5 centimeters. To me, it looks closer to 8.4 than 8.5. And so what would I say about the measurement of this pencil's length? Well, I would say 8.4 for sure. And then I can kind of guess at that third digit, right? So the second digit after the decimal place. So here I guess that it was about 8.42 centimeters. But really only the 8.4 is accurate. The 2 at the end is really just a guess. And so what I would say then is I might jot this down in my notes that the pencil is 8.42 centimeters long, but if I were reporting this number, I would only want to report the measurement that I'm sure about, the measurement that's accurate, and so I would say 8.4. Okay, so it has two significant figures, then 8 and the 4. Okay, and so what if then you're given a measurement and you need to figure out how many significant figures does this measurement have? It's not always super straightforward, but there are some rules. So first rule, anything that's not a 0 is always significant. This is the easy one. So 852 has 3 sig figs. The zeros get a little bit more complicated. So the significance of them depends on their location. So here are the rules for dealing with zeros. First of all, if they're between significant figures, if they're between non-zero figures, they're always significant. So here I have a 0 between an 8 and a 5, and so I would have a significant 0 there and 3 total sig figs. They're not significant if they are to the left of a non-zero digit in a decimal. So what does that look like? Anything where I have a whole bunch of zeros before I have a non-zero number, all of those leading zeros, they're not significant. So I'm showing them in red here to denote that they're not significant. So what that means is in this number 0.085, I only have 2 sig figs. If instead they are to the right of a non-zero digit in a decimal, then they are significant. So if instead I had 0.080, the 0 would be significant at the end. The first two, still not. Okay, and then my favorite, they are ambiguous if they are to the right of non-zero digits in an integer. So what does that look like? That looks like something like the number 800 here. Those two zeros, they are ambiguous. We don't know if they are significant or not. Okay, and so what can we do to clarify? Well, let's take a closer look at why we would need to clarify. Why do we care about these sig figs? Sometimes I feel like it's just, brushed off like, oh, it's kind of annoying dealing with sig figs, but it actually does make a difference. It actually is important to think about sig figs. So let's think about it in terms of these ambiguous zeros. Why are sig figs important? Well, if I told you that driving to Toronto from Cleveland is 200 miles, well, that would be this case where we have the two ambiguous zeros, right? And so I could mean a number of things when I said that drive was 200 miles. I could be telling you 200 where I mean that both of those two zeros are significant, so all 3 digits are significant, and that would mean that the drive is between 199.5 and 200.5 miles long. So that's a pretty clear picture. But more likely in this case, if I'm telling you it's a 200-mile drive, I probably mean that, only that 2 is significant and the zeros are, not significant. So that means the drive is between 150 and 250 miles. And so that's a big difference, right? So if you think about it, if you're driving 60 miles an hour, the difference of 100 miles is over an hour in drive time, right? So this is a big deal to care about your sig figs. So it is important. Maybe you're expecting only a certain amount of time for your drive and then it takes you an hour longer. That would be unfortunate. So sig figs are important. So anyway, this is the problem with the ambiguous zeros. And how do we fix it? We use scientific notation. You might be familiar, I'm probably familiar with scientific notation. It makes our lives a lot easier. So the first case where we had both zeros significant, I would write that as 2.00 times 10 to the second. So basically you take that decimal point, you move it over so you only have one digit out in front of it, and then you multiply by the appropriate power of 10 to give you the number that you started with. And that's how you write things out in scientific notation. So here in terms of our second example where only the 2 was significant, I would say that I only have 2 times 10 to the 2. And so that tells me right away, this guy, it only has 1 sig fig. This guy, it has 3, right? So we can see the difference between those two measurements very clearly. Last example here, I have 5 zeros preceding a 2, 0. And that would tell me I could rewrite that as 2 times 10 to the negative 6. This is a much clearer representation of this number. Counting those zeros makes my eyes cross. And it gets really challenging, you know, if you're doing calculations and you have to write out all those zeros, they get lost pretty easily. So I highly recommend I keep my calculator in scientific notation all the time. It just makes sure that you're not losing any zeros when you're writing things out. It might be helpful. If you like it, go ahead and try it. Okay, so now we know how to look at a number and tell how many sig figs it has, but how do we deal with sig figs when we're doing calculations? So there are a few rules for that as well. And so when we're multiplying and dividing, this is our first rule. It turns out you want to keep the same number of sig figs in your answer as the number in your product or division that has the lowest number of sig figs. So looking at an example, here we have what is your speed, which I'm going to call v, if you travel 7.22 meters, and I'm going to call that distance x, in 5.0 seconds, which I'm going to call t, that's time, and we're going to use the equation v equals x divided by t. Okay, so first thing I want to do here is I'm going to write out x, which is equal to 7.22 meters. And I notice right away that that guy has 3 sig figs. Next, I'm going to write out my time, t, which is equal to 5.0 seconds. And I notice that that guy has 2 sig figs. All right, so then we want to calculate v. v is equal to x divided by t, 7.22 meters divided by 5.0 seconds. Okay, and so if I calculate that out, I actually get 1.444 meters per second. Okay, and now I need to take a look at my two terms that I was dividing in this case. Here, the term with the lowest number of sig figs is the time. It had 2, so I need to round to 2 sig figs. So my final answer here would be 1.4 meters per second. Okay, so I needed to round to my 2 sig figs. Next, what happens if we're adding and subtracting? Well, the rule is a little bit different, and actually instead of looking at sig figs, you look at decimal places. So when you add or subtract, you need to keep the same number of decimal places in your answer as the number in your sum that has the lowest number of decimal places. So let's look at an example of this as well. You travel 96 kilometers in your car, then 220.8 kilometers on a train, and what is the total distance you travel? Okay, so to solve this one, I'm going to say x car is 96 kilometers. Let's take a look at how many decimal places that has. It's a whole number, it has no decimal places, so I would say it has 0 decimal places. Next, let's write out x train. Okay, and it has 220.8 kilometers. Okay, and so here I can see I have 1 decimal place. Alrighty, and then I'm going to do this sum, the total distance you travel. X total is equal to x car plus x train. Okay, and so I would just go ahead and add 96 plus 220.8, and those both have units of kilometers. And when I do that addition, I get, let's see, I need to carry the 1, so I get 316.8 kilometers. Okay, and so now to round this guy, I need to think about which number has the lowest number of decimal places. That must be x car, which had 0. So I need to round this guy to 0 decimal places. That gives me my final answer. X total equals 317 kilometers. Okay, we're all set. All right, so let's wrap up with a few last questions for you to try on your own. So, how many significant figures do each of the following numbers contain? This first guy here, this 0 is significant, right? Because it's between the 2 and the 8. This guy is also significant because it's after the decimal place. All right, so in this case, I would have 1, 2, 3, 4, 5 sig figs. All right, next number. The first 0 is not significant because it's before my decimal. Everything else is non-zero, so I would have 2. Okay, last guy here. I have a whole bunch of zeros. They're all after my decimal and after a significant figure, and so I would say that yes, those all count. They are all sig figs, so I have 1, 5. So 5 again. Okay, so I would say 5, 2, 5, which would give me answer B. One more. How many significant figures will you have in the sum that's written out here? Okay, let's take a look. So actually, I'm going to add and subtract this sum out first because, and really we're just adding here. So I would add this up first because notice to determine the appropriate sig figs for addition and subtraction, you have to do decimal places, but I'm asking for the number of sig figs. So you actually are going to have to add it up, determine the appropriate decimal places, and then go backwards and count the sig figs. So let's add them up first. I did this in a calculator, not in my head. So 1,134.0388. All right, and so now I want to round that to the appropriate decimal place. I'm going to do that by looking at the terms in my sum. Which one has the lowest number of decimal places? I would say that's the first term here. I only have 2 decimal places, so I need to round to 2 decimal places here as well. So I would round that guy to 1,134.04. Okay, last step, count up sig figs. So here, this guy is significant since it's after the decimal place and before a non-zero number, and so I would get 1, 2, 3, 4, 5, 6. Okay, so answer D. All right, see you guys in class.